Swayam Prabha. Digital India. Educated India.
Welcome. So in today's class we will see set cover problem again, but using linear programming, and we will provide another analysis of our greedy algorithm for set cover using linear programming. This approach is called dual fitting. So today's topic is dual fitting. So what is the idea of dual fitting? So this in dual fitting we use LP duality to provide approximation guarantee of a combinatorial algorithm. So we use a linear program not to directly solve it, we use it to analyze it. We are not solving linear programs. So this falls under second approach of using linear program for approximation algorithm design. So the idea is using the linear programming relaxation of the problem of the problem and its dual one shows that the primal integral solution, the solution of the integral solution of the primal is fully paid for by a particular assignment of dual variables. Although that dual assignment may be infeasible. Now, what do I mean by paid for? It means that is a dual assignment say y1 to ym pays for the output of the algorithm. So, there exists an algorithm which we are analyzing. So, for the output of the algorithm, if alg, the quality of the solution, the value of the optimization function of the primal at the output of the algorithm, alg is a minimization problem. So, this is alg is less than equal to summation bj yj, j equal to 1 to m. The value of the dual objective function at y1 to yn. This is value of the dual objective function at y1 to ym. So, this is the first step, and then the second step, the first step is to come up with a dual assignment which may be infeasible, but this gives a bound on alg. And then the second one is scale y1 to yn appropriately so that the scaled assignment becomes dual feasible. This the scaling factor will give us an approximation ratio of the algorithm. So, what we will do next is we will use dual fitting to analyze the greedy set cover algorithm. So, use dual fitting to analyze greedy set cover algorithm. Okay. Why we do that? We already have analyzed it using some other approach, and we have seen that the approximation ratio is log n, but this analysis framework will allow us, we will see that to analyze some similar algorithm for some generalization of the set covered problem, and the analysis will be the analysis of those generalized version of the set covered will be exactly similar. That is the gain. So, for this to apply dual fitting, what we do is that the first step is to write down the linear integer linear programming formulation of the problem. So, here we will solve a more general set cover problem where each set is associated with a cost, and the job is to not to pick the minimum number of sets, it is to pick the set of a collection of sets which minimizes the total cost. So, we need to minimize the total cost of the sets picked. Minimize summation Cs xs. So, we have variable for each set of the set cover instance, and Cs is the cost, and it is a 0 1 variable. So, if the set S is picked, then xs is 1, otherwise it is 0. So, you are summing over all sets in the collection of sets subject to what are the constraints, that each element should be picked. That means, if I look at an element, this is for all element E in U, S in S, such that U belongs to S, sorry, E belongs to S, among all the sets where E belong, at least one of them should be picked. So, xs is greater than equal to 1. This is for all edge. And what is xs? Xs takes value in 0 1. Okay. So, this is the ILP formulation. What we do next is look at its linear programming relaxation. So, LP relaxation is, again the objective function remains same, minimize summation Cs xs S in cal S subject to for each element E in the universe, summation xs S in scal S E belong to S, this is greater than equal to 1, and xs is greater than equal to 0 and less than equal to 1. Now, see that because the objective function is monotonically increasing in xs, each xs, and we want to minimize it, we can safely drop the upper bound on xs, and you can write xs equal greater than equal to 0, and this way the objective function value does not change by dropping the constraint that xs less than equal to 1. So, those constraints are redundant constraints. So, this is the primal linear program LP relaxation of the set cover problem. Now, let us write the dual. So, for dual what we do is that I have a constraint for each element in the universe. So, I will multiply it with a variable, let us call it say ye, and the coefficient of each xs, this is which is Cs, this should give a bound on the coefficient of yi's, coefficient of x is here. after summing all these inequalities. So, what is the goal? The goal is to maximize what? I multiply these inequalities and sum all these cardinality u mean inequalities, and the right hand side we want to maximize, that is summation E in u y e subject to now look at this set X S. Which sets which constraints it belong to? It belongs to all the constraints corresponding to its element. So, the constraint is for all set S in cal S, we have summation E in S y e, this is less than equal to C of S, and we have y of E is greater than equal to 0 for all E in U. You know, this is the dual LP. This is the dual LP, and this one is the primal LP. Okay. Now, we observe that the primal is a minimization problem and its coefficient matrix all entries are 0. Such a program is called the covering program, covering LP. On the other hand, the dual is like, you know, again all constraints are the coefficient matrix has only non-zero entries, and it's like a packing problem. So, this is called a packing LP. So, if the coefficient matrix has only non-negative entries, then the primal LP, which is a minimization LP, primal LP is called the covering LP. And the dual LP which is a maximization is called the packing LP. Now, these LPs often arise in natural problems, and that is why they are given some natural more names. Now, if I write down, so suppose this is here somewhere 0 and infinity. So, here is suppose the optimal integral solution. This is here, this region is primal integral solutions. Now, if I relax it, this is maybe LP opt. So, this region is primal fractional solutions. And this region is dual fractional solutions. Okay. Now, for dual fitting, what is the first approach? The first approach is to bound a alg, the performance of the algorithm with respect to some setting of the dual variable. So, we set ye equal to price of e. So, simply set ye equal to price of e. Then alg, we know this is sum of e in u. This is this because this we described in the analysis of set covered greedy algorithm for set covered. So, this is price of e. This is because whenever I pick a set, its price its cost has been distributed equally among the uncovered elements, among the elements which are newly covered by these sets. Suppose this set has 10 elements, but when it is picked, some 5 elements is already covered. So, it covers new 5 elements and their prices are set to be the cost of the set by 5. So, it is just so the sum of prices of all the elements is the sum of the cost of the sets picked by the algorithm. Hence, alg is sum of prices of the elements, but this is sum of ye in u. But this will be, it is easy to check that this will be an infeasible solution. So, what we define is that we define ye hat is price of e by h of n, the nth harmonic number. We claim ye hat e in u is a feasible solution of dual LP. Now, what we will achieve by this? If it is a feasible solution, it stays somewhere here. So, that means this is a lower bound on opt, and using this we will show that we will show the approximation factor of the algorithm. So, proof. So, we need to show that this set of variables satisfies all dual variables, all dual constraints. That means no set is overpacked. So, we need to show that the assignment ye hat e in u does not overpack any set. Okay. So, let us pick any set. Let S belong to the collection, B any set Again, number the elements in the order they are covered. Number the elements of S the elements of S in the order they are covered. Let S be E1, E2 to Ek. These are the k. Suppose it has k elements E1, E2 to Ek. Now, consider the iteration when Ei is covered. So, we will bound the price of Ei, because price of Ei is set when Ei is covered for the first time. So, consider the iteration when Ei is covered for the first time. In this iteration, only price of Ei is set. Okay. So, whichever set picks it, what is the, if S picks it, if S is used to pick it, then still in that iteration Ei to Ek they are still uncovered. So, if S is picked, then S can cover Ei at a cost of C of S by, and it covers the remaining Ei to Ek elements. So, at least k minus I plus 1 elements it will cover, at least this many new elements it will cover. So, price of Ei must be less than equal to this, because this set S can cover Ei at this price. So, if some other set is picked, then that can be picked only if it covers Ei at lesser price. So, price of Ei is less than equal to this. So, now what is the constraint? So, the constraint here is summation Ye, that means summation Ye1 to Ek should be less than equal to Cs. So, that we need to show. So, Ye1 plus Ye2 plus dot 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 Yek is a hat. This is what? This is 1 by Hn price of E1 plus dot price of Ek. Now, price of, we have a bound price of Ei is less than equal to Cs. So, this is less than equal to cost of S by Hn summation 1 minus k minus I plus 1 I equal to 1 to k. So, this is Cs by Hn times Hk. Now, Hn is at greater than equal to Hk, because k is less than equal to n. This is less than equal to Cs. So, this is a dual feasible solution. So, what do we have? Then opt is greater than equal to any dual feasible solution. So, what is the dual objective? Summation Ye hat. This is summation Y hat is nothing but Ye E in U 1 by Hn. and summation YE here, this is alg. So, this is alg. So, in together we have alg is less than equal to Hn times opt. Hence, it is a Hn factor approximation. It has an Hn factor approximation algorithm. Okay. So, in the next class, we will use this again dual fitting approach to solve a generalization version of set cover problem. Okay. Thank you. So, let us stop here.